Thank you for joining today's session on Introduction to Pumps and Compressors. When folks are developing pumps and compressors, there are some key challenges that engineers face when developing pumps and compressors. And here's a short list below where you can see some of the general goals and challenges include things like optimizing machine performance and efficiency, and minimizing internal leakage of the pump or compressor. And then these machines often give off some noise and some unwanted pulsations. And so engineers are often tasked with trying to reduce that as much as possible. And obviously the machine needs to have longevity, and the bearing supports and the construction of the machine must be well designed adequately for reliability in the field. And also understanding how the machine will perform in a surrounding system is a task, particularly for suppliers, that could be challenging because they're not sure often what the end customer surrounding system might even look like in the field. And understanding how it would perform in a variety of circumstances is a challenge for engineers for sure. And also understanding what happens when you're testing the product, and sometimes certain tests are very hard to do, and that includes things like cold start, for example, and getting a controlled condition at a very low temperature, and trying to understand what happens under those extreme circumstances can be a challenge for engineers. And then also being able to reduce physical testing, as physical testing is expensive, and finding that optimal design of the product as fast as possible so that you can get the best speed to market. And so this is just a short list of some common challenges that we've seen from our customers, and we recognize that multi-physics simulation can address some of these challenges in a variety of different ways. Now, in the realm of CAE simulation and multi-physics simulation, there are a variety of tools at the engineer's disposal, typically. And this is a wide spectrum of tools. And so if you start on the left-hand side, we've seen that engineers often rely on back-of-the-envelope type calculations, Excel type calculations, or even 0D type models representing a pump or a compressor. And these typically calculate on the order of seconds or so. And then there's also the other side of the spectrum, which allows engineers to really focus on deep physics, including the 3D finite element analysis, CFD, conjugate heat transfer, and things like that in 3D. But this can take a simulation to finish on the order of days or even weeks, depending on the scale of the problem. And so, where we envision GT Suite slotting in along this spectrum here is that you can think of a GT being able to span, and we like to think to bridge the gap between the ends of the spectrum, where engineers can go in with a very simple calculation, the Fidelity type model that solves on the order of seconds, and they can then add complexity to the model that allows them to get deeper insight, which adds complexity to the model and scales the runtime, but typically on the order of minutes or so. And so in terms of speed calculation, it's certainly slower than your typical back-of-the-envelope calculation, but much faster than a lot of the 3D tools out there. So hopefully that gives a good overview of that. And when we talk about our company is called Gamma Technologies, and that's where the G and T come from in our GT Suite software name. Gamma Technologies headquarters is outside of Chicago, in a western suburb of Chicago, in Westmont. And we were founded back in 1994, over 25 years ago. And our business is focused exclusively on research and development of a simulation software platform called GT Suite. Now, GT Suite is a transient multi-physics tool, and we'll get into a little bit more about what that means in a minute. And to this day, over 700 organizations around the world are using GT Suite in a variety of different industries. And we are widely acclaimed for world-class local support at dedicated offices, not only at our headquarters here outside of Chicago in the United States, but we also have a office in Stuttgart, Germany, over in Europe, and a relatively new office that opened in Pune, India. And this gives us great local support to speak in the same language and work in the same time zone as our customers. And we also have a great relationship with our representatives at IDAJ, who support our customers in Japan, China, Korea, and Asia. Now, when it comes to compressors and pumps and also system modeling, to give you some perspective on what GT Suite can support, you can see starting on the left-hand side here, we support many different types of machines. We're going to go into more detail about this in subsequent sessions, where we have great capabilities for Vane-style machines, and there's a variety of different types of Vane-style machines out there. Gerotor-style external gear, screws, scrolls, recips, and swashplates, and so on. And so we've even seen a variety of exotic types of compressors as well. And in terms of the systems that are supported, we have a variety of different types of systems that have been simulated in GT, including things like oil and liquid systems, hydraulic systems, but also two-phase type systems, including air conditioning and refrigeration, air-type systems for air compression and vacuum and blowers, and also for process gases and so forth, but also supercritical applications for things like waste heat recovery and so on. And then there are a variety of different fluids that are supported inside GT, including the ability to model a pure gas or a pure liquid or a mixture of gas and liquid, and also for refrigerant type fluids, we have a properties database available from NIST RefProp that's built right into GT. Now, just a general introduction to modeling pumps and compressors. We feel that the GT Suite is uniquely positioned to model positive displacement pumps and compressors for a variety of different reasons. But one of the most common themes is that flow performance, pulsations, and friction can be predicted in these positive displacement machines. And it solves much faster than 3D CFD, while still giving a lot of the same general trends that engineers expect to see in a simulation program. And for many types of these machines, as we'll go through in subsequent sessions, is the ability to build these models very fast, particularly with the aid of 3D CAD setup that allows you to build models on the order of minutes or a few hours. And then the ability to easily integrate the machine into a surrounding system for coupled feedback type studies. And we'll get into more detail about these different points here in a bit. And then also the ability to do structural type problems where loads from the machine can be, due to chamber pressures inside, can be transmitted onto shafts that support the machines, and ultimately to calculate things like bearing loading and performance and so on. Now, the physics behind the solver in GT Suite is the solver is inherently transient, and it allows for unsteady flow due to the nature of the way we solve our equations. And inside the flow solver, we're always solving the Navier-Stokes equations. And so that's the same governing equations you would solve with full 3D CFD, just reduced down to one bulk flow dimension along the axis of a one-dimensional pipe. And so by solving the Navier-Stokes equations, that includes solving for conservation of mass, momentum, and energy, but also conservation of species as well. And that allows for things like species transport. But also there are other sophisticated models inside, particularly for hydraulic applications. It's important, where things like cavitation and free and dissolved gas modeling can be supported in the tool. Now, people often ask, what is GT Suite software? What does it encompass? And this slide here is intended to show the different applications and the typical workflow that an engineer would utilize inside GT Suite. And so in terms of applications, there is a CAD builder that's kind of the very start of the workflow process, and that's using SpaceClaim. And SpaceClaim is included free with every license of GT Suite. And then from there, the CAD builder is typically used to prepare a CAD model by sometimes defeaturing it or cleaning up unwanted solids inside the model, or even doing things like volume extraction to prepare it for going into a GT Suite model. And then once the model is prepared from CAD, it can be imported into our native 3D CAD tool called Gem 3D. And from there, we support importing of not only native CAD formats, but also SpaceClaim format as well. And this is really a great interface where you can take a raw 3D CAD file and discretize it into a fluid model or a thermal model or a mechanical model, and integrate those different physical domains together all in one shot. Now, there are also other UIs that are for pre-processing of a model in GT, and that includes the Converge Light Studio, which again is free in its light form for every license of GT. And then there are also other types of applications, including a valve train design application, and then also a link with a detailed thermal software called Tytherm. Now, once the model's sort of set up from CAD and built with our preprocessors, then the engineer would go to our main model building interface called GTEase. And this is where the engineer will complete the model building process by adding things like boundary conditions and adding different components from our template library, and even adding things like controls to develop a control strategy around the physical model. Now, within this model building interface is also included a built-in optimizer and design of experiments interface that allows you to do very nice parametric studies, do trade studies, and you can hone in and really explore the design space, iterating over hundreds or thousands or even tens of thousands of operating conditions. And then once the model is built and ready to be called by the solver, it launches our multi-physics software solver. And inside the solver is the coupled integrated feedback between different physical domains. And so on the fluid dynamics side, I'd mentioned we are a 1D Navier-Stokes flow solver with also some abilities to do very coarse 3D, pseudo 3D type capabilities. And then on the thermal side, we have the ability to do things like lumped mass modeling of a given structure, or even go into full 3D finite element analysis. And then on the mechanical side, we have a 1D to full 3D multi-body dynamics software built in, as well as 3D finite element capabilities. And then there are other physical domains users can link to as well, including on the electrical side, the ability to model simple and advanced motors, even batteries and electrical circuits. And then oftentimes these physical systems need to be controlled in some manner. And so the ability to manipulate and control the plant model in GT is a very important thing to do. And we can do that with either our controls library built in, or another popular option is to directly co-simulate with MathWorks Simulink. And then for combustion type problems, catalyst type problems and things like that, we have a chemistry library that allows you to do simple and reacting flow with chemical kinetics included as well. And then finally, our software works very well with other commercial codes and in-house codes that allows you to integrate directly and co-simulate with other tools. And then finally, once the model has run with our multi-physics solver, then we can post-process with our GT post-processing interface. And that allows you to do powerful post-processing analysis right in the GT Suite tool. So when users talk about what is GT Suite software, it encompasses all these different applications and all these different physics, all integrated with a seamless workflow. Now, since our software is a multi-physics software platform, it allows these different physical domains to be integrated together, and it really allows the user to harness the power of multi-physics. And you can see this demonstrated here in this schematic of a scroll compressor example, where there are different physical domains interacting with each other. And so for the case of a scroll compressor, for example, you're modeling not only the gas exchange flow path from the intake side all the way through the discharge side, but you're also doing the ability to model things like electric motors to predict not only the torque requirement or the variable speed requirement on the machine, but also since that motor produces some heat, then that heat can also be passed back to the flow system for coupled heating of the fluid. At the same time, that electric motor has some torque, and it's also driving typically a mechanical shaft that ultimately spins these machines. And so the shaft and the supports, bearings and things like that can also be integrated directly with the model. And then additionally, their ability to do things like fluid structure interaction, where reed valves, for example, that it gives you that dynamic feedback between the flow system and the mechanical structure, really delivers valuable insight to the engineers for analysis. Now, in terms of different types of outputs that you could expect from the software of GT Suite, here are just some high-level concepts. And there are typically three main buckets of outputs that users are commonly interested in. Number one being general performance of the machine. And so this includes things by performance, meaning things like mass flow rate, the delivery pressure, and torque demand at or power demand at a given operating condition. And so here at the top left, you can see an SAE paper we wrote several years back on vane pump performance of an oil system pump with GM, looking, and you can see the validation to test data here. Another bucket is the ability to solve for wave dynamics and pressure pulsations from the machine. And here's an example right in the middle, again looking at a GM oil pump, and this time looking at the pulsations, and you can see the comparison to 3D CFD, not only for pressures inside a given chamber, but also delivery pressure pulsations. And what this really allows you to do is it opens the door to doing acoustic modeling and the ability to try to eliminate, or not eliminate, but at least reduce noise emanating from the pump or compressor or machine. And then on the right-hand side is the ability to predict friction in these different machines, as highlighted here with an SHW pump, and where we're looking at overall performance, volumetric flow rate, but also friction, overall friction inside the machine at different operating conditions. And the friction also paves way to being able to do detailed mechanical or structural analysis, where we're solving for things like shaft dynamics and overall mechanical performance of the machine as well. So there are also some things that allow for rapid development of the models, including the ability to, as mentioned before, the ability to take original CAD and bring that into our software to build detailed machinery models very quickly. And then also the ability to really truly understand and visualize what's happening inside the simulation, where you can again start from 3D CAD and you can view results as if it was right on top of that 3D CAD. And as you can see on the left-hand side here, where we got started with some original CAD shapes and then viewing things like temperature or flow fields or pressure fields as if it was on top of the 3D geometry itself. And then there's also the ability to do detailed thermal and mechanical finite element analysis. Here's an example of a single cylinder machine with thermal temperature contours overlaid on top of the FE mesh. Now, on the mechanical and structural side, to dive into this a little bit further, is the ability to solve for multi-body dynamics of shafts and crank trains and compressor mounts and so forth. And there's also a built-in FE solution for bearing film supports as well that allows you to do detailed analysis of particularly hydrodynamic bearings. And you can see an animation of this here on the right-hand side. And then we also have nice friction models and solutions for cylinders and bearings and other types of interfaces between moving parts. And then another common type of analysis here would be looking at reed valve dynamics. And here's an example of a reed valve FSI output that you would see from the simulation. Now, when it comes to shafts and bearings and friction analysis, should dive in a little bit more on this. On the shaft analysis side, we can treat shafts both from a rigid standpoint or torsional or even a full bending approach. And it also allows us to do frequency domain to determine things like eigenvalues and natural and forced responses of a given system. But also, since our software is a full transient time domain solver, it allows you to predict full transient events as well. Another common thing that you might see in the machinery is the ability to do dynamic balancing of different types of shafts and look at things like how much deflection there would be at certain locations along the shaft due to out of balancing and other types of forcing functions on the shaft. Now, those shafts need to be supported, and there's a variety of different models inside the software that allow you to model the bearings. And on the hydrodynamic side, we have different levels of fidelity, starting from a fast-running mobility method to more detailed HD and even elastro-hydrodynamic, both radial journal bearings and also axial thrust bearings as well. Now, roller bearings are also very common in certain types of machinery, and so we have a full 3D roller bearing solution that also comes with a life rating included there with geometry that's typically based off a catalog like an SKF catalog and so on. Now, these shafts can also be linked with drive systems as well to look at things like gear dynamics and then friction that comes along inside the drive system. And then since these machines have a drive torque or drive power that needs to be input to this, the link between the machine and whatever the drive system is that's driving that component, there sometimes could also be resonance that is happening inside that system. And so resonance phenomenon could also be predicted by GT Suite. And then finally, to be able to predict the total power requirement of the machine, the ability to solve for friction at various interfaces, including things like seals and rings, piston surfaces, and just contacts in general can all be supported in the tool to give the user not only an indicated power measurement, but also a total friction or mechanical power prediction as well. Now, these machines also can be integrated into a surrounding system to give valuable insight on coupled feedback to look at entire system behavior. And this includes some examples here that are highlighted below. Include, what happens when, for example, we introduce an economizer onto an AC compressor? What kind of detailed feedback is that giving to the overall system, and how does that change the performance not only of the system and of the compressor? And then another example would be, for example, looking at priming of an oil pump into an oil system. And a common thing is to look at would be on the hydraulic side, this concept of time to prime. And here you can see an example animation showing a system that's initially filled with air, and then it looks at transient filling or priming of that oil system. And the detailed hydraulic pump can be included in that to really give an accurate prediction of the time to prime. And then another common thing task that engineers do as well is to insert a muffler to reduce unwanted noise from the machine. And here's an example of a screw compressor with a muffler attached to try to optimize the noise coming from the given machine. Now, GT Suite also comes with some extra value-added features, and I've spoke about a few of these already, including with every license of GT comes a license of ANSYS Space Claim for CAD building, but also included for free is the light version of Converge 3D CFD integrated directly into GT. There's also a built-in design of experiments that allows you to set up many cases very quickly, and also the ability to post-process those many design points to do meta-model training and so forth. And then we also have a built-in optimizer that allows users to do single and multi-objective optimization. And then when users are cranking through many different operating points, it can take some time to solve. And there's a great feature inside GT that allows users to distribute multiple cases simultaneously to different solver cores to crunch those cases in parallel. This allows you to look at many trade studies while accomplishing the job much faster than serial processing. Now, GT Suite is a flexible and open platform that allows users to integrate and co-simulate with many commercial tools out there, including things like MathWorks Simulinks, or on the CFD side, we support a variety of the commercial tools that are out there. And also on the multi-body dynamics side, the ability to integrate compliance matrices with other tools, including Altair and MSC and so forth. And then on the turbo machinery side, we have some very nice links with partners of ours, including on the centrifugal machinery side, Softenway, on the gerotor machine side, Gerotor Design Studio, and also on the screw machine side, with Scorg. Now, you can also write your own user code. Let's say you've got your own secret sauce that you want to put on top of the GT model. We have the ability to write your own user code in Python or C or MATLAB or also Fortran to integrate with the tool. Now, if you also have a homegrown in-house tool that you would like to link with GT, we have an open API that allows us to link to virtually any tool out there. And then the final thing to mention here about the openness of the platform is the ability to integrate GT with controls for model in the loop or software in the loop, and then all the way to hardware in the loop, where instead of running the controller of your system with physical hardware, in this case being the physical machine, you could replace the physical machine and the heavy costs that come with testing that with a virtual model of that machine inside GT. And so this allows for faster calibration of controls while reducing the physical testing that comes along with the lab requirements for physical testing of the machine. Now I'm going to mention a few selected validation studies for a few different types of machines, and in later subsequent sections we'll be going over more details of these different types of machines. And so the first one we'll start out with is looking at vane pump performance inside an oil pump in an automotive application. And here you can see there's on the left hand side, it's a pivoting style vane pump, and this was written in a SAE paper back in 2014. And the goal of this was to see how predictive GT could be in predicting the performance, including flow rate from the pump, and looking at delivery pressure and dynamic displacement and drive torque requirements for the pump at a given operating conditions. And you can see the agreement is quite good with test overall, as different pump speeds and also different temperatures were studied in this paper. Now, our detailed friction model inside the Vane machine allowed us to really get a decent prediction of the overall drive torque on the pump. And so you can see there's a variety of different components of friction that are included inside this machine to give us that total torque or power requirement. On the gerotor pump side, as was casually mentioned before, is the ability to look at a detailed friction inside a gerotor type machine at a variety of different conditions, including not only as a function of pump speed, but also at different temperatures and at different clearance conditions. And what this does is it really allows the user to look at the trade-off between clearance tolerances for manufacturing and how the performance of the machine will act under those different clearance tolerances. And then the next one is related to a scroll compressor study by Sandin from a European GT conference a few years back. And in this case, the goal here of this study was to try to optimize muffler geometry to reduce the sound and NVH issues that were coming from the scroll machine. And by doing this virtually, it really saves a lot of need on the physical testing of different iterations of the muffler design. And in order to accurately capture the acoustic response of the machine, we would be able to compare to test data that you can see on the right-hand side, looking at things like discharge pulsations, and also looking at the indicator diagram, and also things like discharge valve dynamics. And you can see the agreement to test data here on the right-hand side is quite good. Fast forwarding to another type of study. In this case, it's a screw machine. And in this case, it was also a two-phase expander where the machine is not assuming just a pure gas or a pure liquid. In this case, there's actually a two-phase fluid flowing through the machine, and this was written by Dr. Bianchi a few years back in the towards the International Journal of Refrigeration. And what was interesting about this was analyzing the performance of the machine at different quality operating conditions at the entry to the machine, and optimizing, what quality would be best suited for the problem, and what types of refrigerants are best used for this type of machine. Sticking with another compressor, in this case being a reciprocating compressor for an air conditioning or refrigeration type, in this case a refrigeration type system. And you can see the detailed component modeling, not only solving just the bare compressor, but also all of the piping on the suction side and the discharge side that influences the noise coming from the compressor. And then the model looked at, you can see, resolving these different flow volumes with a pseudo 3D, coarse 3D mesh. And you can see with these different cells that are representing the physical geometry. And you can see by taking this sort of coarse 3D approach, the ability to accurately resolve the pressure that's exhibited in the machine is quite good, while at the same time being able to solve very quickly. And then also wanted to mention about Swashplate pump pulsation validation that was done. In this case by Caterpillar, who had presented at our user conference a few years back. In this case, you can see these hydraulic pumps need to operate in a wide variety of testing conditions, all the way down to -40°C, and you can see the extreme case here of this large mining truck that's completely covered with ice. I wouldn't want to be starting up in that condition for sure. And then all the way to the full hot operation as well. And the pump needs to perform over this drastic temperature range. And so the simulation was done with GT, and things were compared to measurement, including pressure pulsations, but also torque required to move the pistons, and to predict. In this case, it was a dynamic Swashplate piston pump, where the Swashplate angle can be predicted, and you can see the agreement to test is quite good here, with also looking at transient cold startup, where the speed here is changing over time, and you can see the torque, the drive torque requirement comparison between test and simulation is quite good. Now with that, I'll open it up to a brief software demonstration showing users where you can go to access a variety of different examples and tutorials inside the software. And so from here, the next step will be to show just a very quick demonstration of some examples that we have related to pumps and compressors. And we'll be addressing different types of pumps and compressors in subsequent sections here. And so first begin by showing the screen where we're looking at, in this case, the primary model building interface called GTEs. And in this case, for those that are not familiar with GT Suite, the model of the physical system is built using templates from our template library and stitched together on this model map here to represent a physical system. In this case, what we're looking at is an example of a gerotor pump, and you can see that under the file menu under examples. And then under examples, we have a library of different pumps and compressors that are available for the users. And it ranges depending on the machinery type. And so in the case of the gerotor pump, the example that we've got on the screen here would be this gerotor pump with relief valve. And so if we open that model up, you can see the different components being simulated here. And you can see these components all come from this template library where you can access different physical models divided by physical domain. And the physical domains include the physics of fluid flow, physics of mechanical systems using 1D to full 3D multi-body dynamics, and then the physics of heat transfer, including all three modes of heat transfer and so on. And then there's also an electromagnetic domain, a controls domain for PID controllers and links to external models, and then also an acoustics library as well. And so, for example, just to give users an idea of how this works is that, let's say users wanted to model flow in a pipe. We would come in here, we would search for pipe, and then we would just drag that pipe right onto the model map, and then start defining dimensions about this physical component. In this case, it's a pipe, so it has a diameter and a length and some heat transfer to the wall and so forth. And so you would start building your physical system this way. Now, in the case of gerotor pumps and other types of pumps, the chambers inside the pump are modeled with a unique flow volume. In this case, you can see this gerotor pump has 5 pumping chambers, and you can see these 5 pumping chambers here, modeled as unique chambers. Now, to model these chambers, evolution of chamber volume, and then port area profiles or schedules and so forth to model this in 1D. The user must prescribe what those volume and port area profiles look like. And that's typically done inside this shaft template called the fluid machine shaft, or for specific types of machines, we have shafts dedicated specifically for things like Vane style machines and Swashplate and so on. For the case of the gerotor pump, you can see the user comes in with a prescribed chamber volume profile. And you can see that right here. And then also this chamber volume profile has a communication to inlet porting. And you can see, for example, the inlet port profile here. And then also the outlet port as well. And so each of these chambers undergoes the same volume and port area schedule, just phased by the cycle duration, which is typically 360 degrees, divided by the number of chambers on the map. And so we have a nice example here of a gerotor pump, and that's already set up and ready to go. And so users can actually hit the run button. Users can also see what kind of boundary conditions are being used. In this case, you can see that this is a speed sweep, simulating multiple speeds. And then when the user wants to set up the model and get it ready to run, you would hit this run button to launch our solver. For the sake of time, I won't do that for this example. And then once the model is finished, and for most of our examples, we have models with results that are already ready to view. And you can access that by hitting this View Results button. And so when we open up this example, it launches our GT post processor and allows the user to really analyze what's happened in the system. And so, for example, one of the things we might want to look at first is what does the volume and port area and leakage area schedules look like? Here you can see that reported on top of each other. And so since there's 5 chambers here, we have 5 unique volume and port area profiles that are generated from the solver. Now, users might also want to say, okay, on an average basis, what does the average flow rate look like through the machine? What does the average pressure rise look like through the machine? In this case, it's a fixed restriction on the outlet. And so as the speed increases, the pressure rise will increase as well. And then also, what is the total power requirement of the machine, and you can see that here. And so there's really good information that can be accessed by the user here. Another one as well would be looking at the chamber information. And so looking at, for example, pressure as a function of crank angle, temperature changes, density changes. In the case of hydraulic pumps and things, the ability to look at how much free gas or cavitation has occurred inside a given chamber. And you can see this at different variety of conditions here, and so forth. Now this is just one example with the gerotor pump, but I want to just show you that there's a library of different examples available right under this Pumps, Compressors, Expanders Predictive. And we'll go through each of these different types in subsequent sections. And then for some of the machines, there is the ability to simulate and start from full 3D CAD. And there are actually written tutorials that go through the process step by step on how to build some of these models. And you can see that under the tutorials menu, graphical applications, GEM 3D. And then for the case of Vane style machines and gerotor style machines, there are dedicated tutorials. And you might have to hit this other button to actually illuminate the PDF document that shows the step-by-step process there. Now, this is just a very high-level overview of our pumps and compressors, and look forward to speaking in subsequent sections here. And then to wrap up this portion of the document, I want to just mention that in terms of training, we have various ways of getting users up to speed. And so one of the biggest things is our unrivaled technical support that's included free with the license. And so we encourage all of our users to interact with the support team here at GT to give you confidence going forward in simulating your different systems. And so here you can see a few testimonials from some of our users and proudly giving praise to the support. But there's other mechanisms beyond our technical support that can get you up to speed. And that also includes, in the cases, typically in-person training once a month at our local offices in Illinois and also in Germany and India. And check out our website for more details on that. But as you've seen here, there are many examples and tutorials that are embedded directly in the software. And also know that for any given system that you're trying to build, you're usually not starting from scratch if you're interacting with the GT team. We're happy to assist you in building baseline models to make sure that you do have confidence in using the tool. And then finally, it's worth mentioning that there's custom on-site training also available for all of our customers and at our disposal. And so thank you very much for watching, and please visit our website at gtisoft.com, or you can also search for more videos that are available on YouTube and so forth. If there are any questions, please contact support@gtisoft.com. Thank you very much.